And now we have the second talk of the session. Yoji Tomita will talk about fast and examination agnostic reciprocal recommendation in matching markets. And this is a regular research paper.
Okay. Hi, everyone. My name is Yoji Tomita from Cyber Agent. It's my honor to present my work, Fast and Examination Agnostic Reciprocal Recommendation in Matching Markets, which is joint work with my colleagues Riku Togashi, Yuriko Hashizume, and Naoto Osaka. Here's the introduction. We consider reciprocal recommendation systems in matching markets, such as job recommendations or online dating, or other services. In RRS, one side of users, like job seekers, receives recommendation of other side of users, like job posts. There are two important aspects which are crucial, especially for RRS. First, it's the mutual interest of users. Even if one job seeker has a strong interest in one job post, the job post might not be interested in the candidate at all. In this case, recommending that job post to the candidate would not be effective. Second, we need to avoid congestion or concentration of recommendation opportunities on popular users. One user can make contact with only several users because of physical reasons, so it is not effective to concentrate recommendation opportunities on a few popular users. Widely used methods in practice cannot deal with these two aspects well, while recent studies are not practical because of some computational issues or assumptions of the model. So we propose a method based on TU matching, which is used to analyze marriage or labor markets in economics for RRS, which deals with the two aspects and is more practical than the recent methods. Then we explain the problem settings following the framework of CUO 2022. We take an example of job posting platform, which recommends job posts to job candidates. We assume that the platform already has the estimators of preference scores of the candidate C toward job J, which is represented by PCJ. And the opposite side of preference, the preference of the job J toward the candidate C, which is PJC. The score is computed by some standard methods like matrix factorization. Here, the platform objective is to maximize the overall expected number of matches. In order to maximize the number of matches, the platform chooses an ordered and personalized job list sent to each job candidate based on the estimated preferences, PCJ and PJCs. Then each candidate applies to possibly multiple jobs. Here, following the study, we assume that their actions are based on a simple position-based model. She applies to job J located at kth slot with probability Vk times PCJ, where Vk is a decreasing examination function of the position K, such as 1 over K. That is, the candidates are likely to apply the job post in upper position. After the candidate's application, the platform sends a list of applications for each job post. In this phase, we assume that these lists are sorted by the job's preferences in the descending order. Job post actions are also based on the PBN. Job J chooses to match with with the candidate C located at kth position with probability Vk times PJC. Here, match means calling for job interview or others. Then the number of matches in this market is determined. This is overall market procedure. So the platform chooses the list sent to each candidate in the first phase to maximize the number of matches. Next, we explain the 3 existing methods for the problem, which is widely used in practice or recently studied. First one is what we call naive method. The platform sends a job list sorted in the descending order of the candidate's preference, PCJ. It maximizes the expected number of applications and is very fast and easy to implement in practice. However, it does not take care about the mutuality of preferences. In addition, popular jobs are likely to be recommended in upper positions for many candidates, and this results in congestion of applications. The second one is the reciprocal method, we call. It recommends jobs in the descending order of reciprocal scores, which is computed by aggregating both sides of preference scores, PCJ and PJC, by some function. As an aggregation function, the product of the scores is commonly used in practice and in studies. It is also very fast and easy to implement in practice, and it can take care about the mutuality of preference because it recommends a job to a candidate only if they are interested in each other. However, it is reported that it could rarely reduce the congestion for the popular users. Third one is the approximate social welfare maximization proposed by CUO 2022. It aims to maximize the social welfare, which is defined as the expected number of matches. However, since maximizing the social welfare is intractable, they derived the lower bound of the social welfare function, and they propose to maximize it by some constrained convex optimization method. It can take care about the mutuality of user preferences and reduce the congestion for popular users relatively. But this method is, we think, is difficult to implement in practice. One reason is the time or space complexity. It needs to solve the constrained convex optimization with C times J squares variables, where C is the number of candidates and J is the number of job posts. Another reason is that it requires the knowledge of the specific form of the examination function, V, since it uses the form of function V in its objective. It depends on the specific service and could be different among users, so it is not easy to estimate in practice. Now we turn to our proposed method, TU matching recommendation. Matching with transferable utility, or TU matching, we use especially Cho and Show model, is a matching market model applied to analysis of labor markets or marriage markets in the field of economics. In this model, agents' utilities are defined as follows. If C and J are matched, they get PCJ plus epsilon CJ plus tau CJ, and PJC plus epsilon JC minus tau CJ, respectively. Here, epsilon CJ and epsilon JC are random variables derived from some continuous probability function f, and it can be interpreted as the estimation error of the preference scores. Here, in the TU matching model, we assume that if C and J are matched, monetary transfers are occurred between C and J, explicitly or implicitly. For example, wage in the labor market, or gifts or income sharing in the marriage market. Tau CJ is the amount of the monetary transfers between C and J. In the market equilibrium, these tau CJs are adjusted so that the demands from both sides are coincided, just like the market prices in the standard economic markets. We call mu with the following conditions as a fractional matching. First, for each Cj, mu Cj is between 0 and 1. We can interpret it the probability with which the candidate C and the job J are matched. Second, mu C0 and mu 0J are between 0 and 1. It is the probability with which C or J remains unmatched, respectively. Third, for each C and J, the sum of matching probability equals 1. This constant 1 is not essential. It could be other constant value, but to cap the matching of each agent, we expose this condition. Now we can define the equilibrium matching. A fractional matching mu star is an equilibrium matching with transfer x tau star if for each Cj, the matching score mu star Cj equals the stochastic demands from both sides. That is, we consider that each agent chooses one opponent that maximizes their utilities given their preferences and transfers. The left term is the probability with which the candidate C chooses job J, and the right term is the probability J chooses C. In equilibrium, these stochastic demands from both sides should be coincided and equals to mu star Cj. These stochastic demands are adjusted in the market by the transfers tau star. So we consider recommending jobs to each candidate according to this equilibrium matching score, mu star Cj. To compute the equilibrium matching efficiently, we assume that the errors distribution, F, is the type 1 extreme value or Gumbel distribution. With this assumption, we can derive the equilibrium matching by the following procedure. First, initialize AC and BJ equals 1 for each C and J. Then repeat the following update of AC and BJ until convergence. We note that the computational cost of each update is the order of C times J, which is faster than the social welfare method. Finally, the equilibrium matching score is computed by the last formula. Finally, we report the results of our experiment briefly. First one is a simple experiment with synthetic data. There are n job posts and 1.5 n candidates. Here we report the case of n equals 50, 100, 200, and 500. Each has the same examination function, Vk equals 1 over k. Preferences are the convex combination of two components. The first term, P over J, and P over C represents their overall popularity of job J and the candidate C. And P tilde Cj and P tilde Jc represent their specific preferences, where each term is derived from U01 independently. We compare the performances in terms of the expected number of matches computed by the Monte Carlo simulations of the market procedure. As a result, TU outperforms the conventional methods like naive and reciprocal methods and performs almost as well as social welfare. We note that the social welfare method does not work for the case of n equals 500 because of its computational complexity, while our method does work in that case. Second, here is the experiment with synthetic data and misspecified examination functions. The setting is almost the same with previous one, but here we test other examination functions. Vk equals 1 over log 1 plus k, 1 over k, and exponential of 1 minus k. We compare our methods also with the social welfare methods with misspecified examination functions, swlog, swimp, and SW exponential, which uses log, imp, exponential functions as the examination functions in their objectives. As a result, TU performs as well as most social welfare methods, while in some cases it could outperform some misspecified social welfare. Finally, we report the experiment with real-world data, which is from one of Japanese online dating services. The profiling scores are computed from the real-world data by matrix factorization. To run the Monte Carlo simulations, we subsampled 200 times 200 and 1,000 times 1,000 data. Both have male and female users' proactive data. Please see our paper for detailed sample procedure. Results are that our method is as well as or better than the naive and reciprocal method. Also, it is slightly less performance than social welfare in the n equals 200 cases, but TU works very well in the case of 1,000, where social welfare does not work in that case. Here is a summary. That's all of my presentation. Thank you for listening.
Thank you. Do we have any questions from the audience? Go ahead.
Hi, thanks for the nice talk. So this problem formulation of two groups with different preference lists, it seems similar to things like the stable marriage problem that Akamai uses for their traffic routing in CDNs. Are there any unique challenges for the recommender setting versus other applications with these marriage matching algorithms?
That's a good point. And in the other application of stable matching problems, like the score matching is a very popular application. In that application, the institute can match the agents as a central institute. But in the web applications like online dating or job recommendation, we can only recommend, but we cannot, in the usual services, we cannot match the, we need to make a long list of the recommendations. That is a slightly different point of the other applications, we think.
I see. So it's because it's users, there's less definition on their behaviors compared to other applications. Is that what you mean?
Yeah.
Okay. Thank you.
Hello. Thank you for your talk. I had a related question. So something we talk a lot about when we talk about stable matchings is the incentive compatibility that comes with the choice of algorithm. Is there any results or intuitions as to whether these types of algorithms that you discussed are incentive compatible, or would they create incentives for users to maybe do something to put themselves as recommendations for better jobs and stuff like that?
Thank you for your questions. In the stable matching problem, the stability and the incentive compatibility is very important. But we did not conducted any other experiments or the analysis of like that. So I do not have the good answer for that question. So it remains in the future questions.
Thank you.
So we have two questions online. One is, have you considered adding budget constraints for Tau?
Not here. We did not adding budget constraints. So
Okay. And the next question is, can you provide any insight on your Monte Carlo optimization simulation strategy? Have you thought of investigating a Pareto-based Monte Carlo simulation?
We did not do the Pareto-based Monte Carlo simulations, so it remains a future question.
Okay. All right. Thank you. That's our second talk for the session. Now moving on to going beyond local, global graph enhanced personalized news recommendation. And this is one of the best paper candidates.